Hello everyone, this is a challenge question walkthrough for Edexcel's Pure Year 2 textbook, Chapter 3. First question is from exercise 3a. The nth term of an arithmetic sequence is un equals ln a plus n minus 1 times ln b, where a and b are integers, u3 equals ln 16, and u7 equals ln of 256. Find the values of a and b. So first of all, if we know that u3 equals ln 16 and u7 equals ln 256, then we know two facts involving a and b. So the fact that we know u3 equals ln 16 means that ln 16 equals, using this formula here, so u3 is when n equals 3, so ln 16 equals ln a plus 3 minus 1, which is 2 times ln b. And doing the same for u7, we know that equals ln of 256. So ln of 256, again using the formula, is ln a plus 7 minus 1, lots of ln b. And from here, we need to solve these two equations simultaneously. And here the easiest way to do that is to subtract the two equations from one another first. So if we do it as the bottom one, take away the first one, then on the left hand side we're going to have the ln 256 take away ln 16, and the ln a's will cancel on the right hand side and we'll be left with 4 ln b. And then using laws of logarithms, we have 4 ln b equals, and if we're taking away logarithms, then we're going to divide. So ln of 256 over 16, and then that gives us a quarter ln of 16 for ln b. And from here, we can take the quarter and put it inside the ln by raising to the power of a quarter. So we have ln b equals ln of 16 to the power of a quarter, and that gives us ln 2. So ln b equals ln 2 means that b must be equal to 2. And now from here we can plug into either one of the two equations, and the first one here is simpler. So if we put in b equals 2 into this first equation here, we have ln of 16 equals ln of a plus 2 ln of 2. And again here we can use the power rule to bring this 2 inside the logarithm. So then we have ln of 16 equals ln of a plus ln of 2 squared, which is 4. And then here again we can get ln a by itself, so taking away the ln 4, and using the log rules we have ln of 16 over 4, so ln a equals ln 4, and then we have a equals 4, and those are our values of a and b. Okay, and our next question comes from exercise 3b. An arithmetic sequence has nth term un equals ln 9 plus n minus 1 lots of ln 3. Show that the sum of the first n terms equals a times ln 3 to the power of n squared plus 3n, where a is a rational number to be found. So, first of all, let's note the sum of the first n terms from an arithmetic sequence, which is n over 2, lots of 2a plus n minus 1, lots of d. Okay, and for this arithmetic sequence, we can see from this nth term that we have the first term being ln 9 when n equals 1, because then we have 0, lots of ln 3, and then the number of terms we're going to keep as n. And also we have the difference here is going to be ln 3. So the distance is ln 3, because that's what we're going to add on every time we move to the next term. Okay, so using this formula for the sum of the first n terms, we're going to get n over 2, lots of 2 times a, so 2 ln 9, plus n minus 1, lots of the difference, which is ln 3. Okay, And now to simplify into this form that they require, we're going to have to do some work with some logarithms. So we know that this 9 here we can write as 3 squared, and then we can bring this power of 2 down outside of the logarithm. So then we have n over 2 lots of 4 ln 3, and we're going to add onto that n minus 1 lots of ln 3. And then at this point, we can factor out ln 3. So we've got n over 2 lots of ln 3, and inside the bracket, we're going to have 4 plus n minus 1. And if we simplify that bracket, we're going to get n plus 3. So n over 2 ln 3 times n plus 3. Now we're almost there, but we want to try and get this into the form a ln 3 to the power of n squared plus 3n. So we need to have the n squared plus 3n, which comes from the n and the n plus 3, and we need to bring that into the logarithm as a power. So here we're going to have a half ln 3, and then we're going to bring the n times n plus 3 as a power, and that gives us the n squared plus 3n. So our value of a is going to be 1/2. Okay, and our next question is from exercise 3e. The sum to infinity of a geometric series is 7. A second series is formed by squaring every term in the first geometric series. Part A asks us to show that the second series is also geometric. So, if we think about what a general geometric sequence looks like, we're going to have first term A, and then after that we're going to multiply every term by r squared as we move along. So we're going to have ar squared, ar cubed, and so on. Then, when we square each of these terms here, then we're going to have, first of all, a squared, then a squared r squared, then a squared r to the power 4, a squared r to the power 6, and so on. And we can see that this also forms a geometric sequence. So this is a geometric sequence with first term a squared and a common ratio of r squared. Okay, now for part B, we're told that the sum to infinity of the second series is 35, and we're asked to show that the common ratio of the original series is 1/6. So, we're given 2 bits of information in the question that we haven't used yet, so here and here. Now we can use the formula for the sum to infinity, which is a over 1 minus r. So for the first sequence, that's exactly the formula. Then if we adapt it for the second sequence, then we're going to have a squared on the top and 1 take away r squared on the bottom. And we're told that this first one up here is equal to 7, and this one down here is equal to 35. And then we now need to solve these two equations simultaneously. So I think we'd be better off starting with this first equation here and trying to substitute that into the second one here. So rearranging that first equation there gives us a equals 7 lots of 1 minus r. And if we plug that into the second equation, we're going to get a squared, so that's 49 lots of 1 minus r squared, over 1 minus r squared equals 35. And this denominator we can factorize using a difference of 2 squares. So we have 49 lots of 1 minus r squared over 1 plus r, 1 take away r, that equals 35. And here we can cancel 1 factor of 1 minus r. And what we're left with there is 49 times 1 minus r over 1 plus r being equal to 35. Then multiplying both sides by 1 plus r. And if we expand the brackets on the left-hand side as well, so we have 49 minus 49r equals 35 plus 35r. Then we've got 49 minus 35 on the left-hand side gives us 14. And taking the 49r onto the other side, we get 84r. And then dividing by 84 on both sides, we then get r equals 1/6 as required. Okay, and my next question is from exercise 3f. Given that the sum from r equals 1 to 10 of a plus r minus 1 times d is equal to the sum from r equals 11 to 14 of a plus r minus 1 times d, show that d equals 6a. So here we're going to have to use the formula, the sum of first n terms is equal to n over 2 times 2a plus n minus 1 times d. So if we jump straight into this first part of the equation, this is going to be the sum of the first 10 terms. So we have 10 over 2 times 2 times the first term plus 9 lots of the difference. So that is 5 lots of 2a plus 9d. And if we expand brackets, that gives us 10a plus 45d. Now for the second part of the equation, this we're going to have to use two different summations and take the difference. So the sum from r equals 11 to 14 means we have to do the sum from 1 to 14 and take away the sum from 1 to 10 to leave us with 11 to 14. So this is going to be equal to 14 over 2 times 2a plus 13d. And then we're going to take away s of 10, which we've already worked out down here. So we're just going to take away 10a plus 45d. This gives us, expanding the brackets here, we have 7 lots of 2a, so that's 14a, and 7 lots of 13d, which gives us 91d, and we're taking away 10a and 45d. So we have 4a, and we're adding on to that 46d. Now to finish off the question, we just set these two equal to each other. So 10a plus 45d, we're going to set equal to 4a plus 46d. And rearranging, we get 6a equals d, as required. Okay, so this question from exercise 3h says the sequence of numbers u1, u2, u3 is given by u n plus 2 equals 1 plus un plus 1 over un. And u1 equals a, u2 equals b, where a and b are positive integers. And part A asks us to show that the sequence is periodic for positive a and b. So if we have a go at trying to find u3, that is going to be equal to 1 plus u2 over u1, so that equals 1 plus b over a. Now if we look for u4, that's going to be 1 plus u3 over u2 now. So that gives us 1 plus b over a, all over u2, which is b. And if we multiply top and bottom by a here, to get rid of this fraction on the top, we're going to have a plus 1 plus b over ab. And now if we find u5, we're going to get 1 plus u4 over u3. So 1 plus a plus 1 plus b over ab, all over u3, which is 1 plus b over a. Now here, if we multiply top and bottom by ab to get rid of the fractions, we're going to have ab plus a plus 1 plus b, all over b times 1 plus b. And now if we try and find u6, we're hoping we might find the pattern soon. So with u6, we have 1 plus u5 over u4. So that gives us 1 plus ab plus a plus 1 plus b over b times 1 plus b, all over u4, which is a plus 1 plus b, all over ab. And now if we multiply top and bottom by a b times 1 plus b, so ab 1 plus b, and then we're going to have a lots of ab plus a plus 1 plus b, all over, and then we're multiplying by ab times 1 plus b, so we're going to have 1 plus b lots of a plus 1 plus b on the denominator. Now this is already starting to look a bit complicated, so let's try and expand the brackets and hope that stuff simplifies. So here we have ab plus ab squared plus a squared b plus a squared plus ab on the numerator, and we're dividing by 1 plus b times a plus 1 plus b on the denominator. So on the numerator, if we sort of tidy that up a little bit, we have ab squared plus a squared b plus 2ab plus a squared plus a. We have a plus 1 plus b plus ab plus b plus b squared. Okay, and now if we factor out a from the numerator, we have b squared plus ab plus 2b plus a plus 1. And this is all over the denominator, which is actually also b squared plus ab plus 2b plus a plus 1. So, woohoo, these two cancel, and we're left with just a. So we have that u6 is equal to a. Okay, now to show this is periodic, we have to show that u7 equals b then. Because then when we find u8, we're going to start all the way from the beginning with 1 plus b over a. And then to find u9, we're going to use u8 and u7, and the whole thing is going to repeat. So we need to find u7, and hopefully this turns out to be b. So from before, we know that u5 was equal to ab plus a plus b plus 1 over b times 1 plus b. So if we plug that into the formula for u7, we can have 1 plus u6, which is a, all over u5, which is ab plus a plus b plus 1, all over b times 1 plus b. So again, to get rid of the fraction in the denominator, we're going to multiply top and bottom by b times 1 plus b. So b times 1 plus b times 1 plus a, all over ab plus a plus b plus 1, that equals u7. And now if we expand brackets on the numerator, we're going to have b lots of 1 plus a plus b plus ab, all over ab plus a plus b plus 1. And again, you can notice that the factor here and the denominator are equal, so we can cancel them out and we're left with just b. So we've shown that the sequence is periodic, and the order of the sequence means how many terms you have to go through before it cycles again. And so we go from u1 all the way up to u5, and we hit the same sequence from u6 up to u10. So the period of this sequence is 5. And our last question is from mixed exercise 3. A sequence is defined by the recurrence relation un plus 2 equals 5 un plus 1 minus 6 un. Part A asks us to prove that any sequence of the form un equals p lots of 3 to the power of n plus q lots of 2 to the power of n, where p and q are constants, satisfies this recurrence relation. So we can start by finding what un plus 2 and un plus 1 are going to equal before we sub them into this recurrence relation here to show it's true. So un plus 2 is going to be equal to p times 3n plus 2 plus q lots of 2 to the power of n plus 2. And similarly for un plus 1, we're going to have 3 to the power of n plus 1 and q times 2 to the power of n plus 1. And now we can substitute that into the recurrence relation they give us. So we're going to have un plus 2 equals 5 lots of un plus 1 and then we're going to take away 6 lots of un, so p times 3 to the power of n plus q times 2 to the power of n. And now if we expand brackets, we're going to have 5p lots of 3 to the power of n plus 1 plus 5q lots of 2 to the power of n plus 1 minus 6p lots of 3 to the power of n, and take away 6q lots of 2 to the power of n. Now we want to show that this here is equal to un plus 2, which is p lots of 3 to the power of n plus 2 plus q lots of 2 to the power of n plus 2. And to do that, we need to change these so they are to the power of n plus 2. And to do that, we need to adjust the coefficient before them. So if here we want 3 to the power of n plus 2, then we have to divide by 3 in before to make up for the extra power of 3. So we're going to have 5p over 3 lots of 3 to the power n plus 2. So we've multiplied by 3 here, so we have to divide by 3 here. Okay, and then doing the same for 2 to the power of n plus 1, we're going to have 5q over 2 lots of 2 to the power of n plus 2. And then for the 6p times 3 to the power of n, we need this to be 3 to the power of n plus 2. So we're going to have to divide by 3 squared, which is 9 on this side. And doing the same for 6q times 2 to the power of n, we're going to have 6q divided by 2 squared, which is 4, lots of 2 to the power of n plus 2. And now if we collect terms, so we have 5p over 3, and we're taking away 6p over 9, lots of 3n plus 2. And then we've got 5q over 2, and we're taking away 6q over 4, lots of 2 to the power of n plus 2. And then if we simplify the coefficients, we'll see that this equals p times 3 to the power of n plus 2 plus q lots of 2 to the power of n plus 2 as required. Okay. Now for part B of the question, we're given that u1 equals 5 and u2 equals 12, and we're asked to find an expression for un in terms of n only. So now we know that u1 equals 5 and u2 equals 2. We can gather two pieces of information about p and q using the formula for un that we proved in part A. So this is equal to p lots of 3 to the power of n plus q lots of 2 to the power of n. And we have u1 equaling 5, so p times 3 to the power of 1, so 3p, plus q times 2 to the power of 1, so 2q. And doing the same for u2, we have u2 is equal to p times 3 squared, so 9p, and q times 2 squared, which is 4q. And u1 equals 5 and u2 equals 12. And now we have two simultaneous equations in p and q, which we can solve. And I think the easiest way to do that here is to take 2 and take away 2 lots of 1 to cancel the q's. So we've got 9p take away 6p gives us 3p. And the q's cancel. On the right hand side we've got 12 take away 2 lots of 5, which gives us 2. So p equals 2/3. And using the first equation, we have 3 times p, so 2, plus 2q equals 5, so q equals 3/2. And those are our solutions for p and q. And part B asks us to find the expression for un. So all we have to do is put in these values of p and q into this formula here. So we've got un equals 2/3 lots of 3 to the power of n plus 3/2 times 2 to the power of n. Okay, and part C, the final part, asks us to determine the number of digits in U100. And using the formula here, we've got this is equal to 2/3 times 3 to the power of 100 plus 3/2 times 2 to the power of 100. And putting this into your calculator gives you 3.436 times 10 to the power of 47. So we're multiplying 3.436 by 1047 times. And if we think about what this number looks like really carefully, we can see that this will have 48 digits. And that is the end of the challenge question walkthrough for Edexcel's Pure Year 2, Chapter 3. I hope you enjoyed this video and I'll see you in the next one.